Welcome to solverfy.
This is chapter 27, problem number 42. We have a closed loop, rectangular loop of wire. This is the direction of the current. It's embedded in an external magnetic field that is into the page here. We know the magnitude of the magnetic field, 1.5 Tesla. We know the length of this rectangle. It's 35 centimeters. And the width is 22 centimeters. We know the current passing through this loop of wire, 1.95 amps. Now, in part A, we are asked to calculate the net force acting on this closed loop of wire. In order to figure that out, let's break the force into segments. So let's say for this side, this is segment 1, from here to there. In order to calculate the force, let's call this segment 2, 3, and 4. Now, when we look at the direction of the force for the first segment, let me use a different color. As you know from the right-hand rule, your thumb is along the direction of the current, which is down, and B, the rest of your fingers are aligned with B into the page. So curl your fingers 90 degrees. You're going to see that this force, let's call it F sub 1, in magnitude, it's going to be equal to I, well, the length, the current times the length of this wire, which is W, right? Times the magnitude of the magnetic field, times the sine of the angle between I and B, which is 90, so I'm dropping that. So the force exerted on segment 1 is IWB. Now let's go across to segment 3 real quick. Let's get that out of the way. This is the direction of the current I. If you use the right hand rule again, we're going to see that F, let's say 3, is actually along the opposite direction of F1. However, magnitude wise, they're equal to each other. So let's try and calculate the magnitude of the force exerted on segment 2. Again, this is the direction of the current. If we align our thumb with the direction of the current and the rest of the fingers along the direction of B, curl your fingers 90 degrees, you're going to see that F2 is actually up, and the magnitude would be IL this time. Little l, we called it this guy. IL times B, and sine of the angle between I and B. As you know, it's 90, so I'm dropping the sine term. When we go to segment 4, then F4 is going to be down, but again, ILB is going to be the magnitude. So as you can see, when we're calculating the F net, we're basically doing F1 minus F3 along x direction. Let's call this x. F1 minus F3 is going to give you 0. And F net along y direction, by the way, I'm using this convention. This is y, positive y, negative y, positive x, and negative x. So then F net along y direction is going to be equal to F2 minus F4, which is 0 again. From here, overall force acting on this loop has to be equal to 0 then. Now, when it comes to torque, let's remember the equation for torque. I times B times A times sine of the angle between A and B, right? So in this case, the direction of A is actually out of the board towards us. This is the direction of A. The direction of B is, as you know, into the board. So the angle between the two, theta, is basically 180 degrees. And sine of 180, it has to give you 0, making the entire torque 0. So this is the answer to part A. In part B, this portion is a tiny bit more complicated. Now there is the loop is rotated 30 degrees around an axis, around the axis. Axis being, okay, this is the loop, the axis, this is vertical axis. So from the top view, actually what's going on, if we look at it from here, is that this is the initial position of the loop, right? So then we're tilting from the top view, we're tilting our loop 30 degrees with respect to horizontal. So this angle is going to be 30 degrees. What is that going to change? We're going to see. So actually force-wise, F net, it's not going to change anything. Still, we have to have net force equal to 0 because of the same reason as we discussed in part A. If this is F1 and this is going to be F3, again, they're the same in magnitude. So F net overall has to be equal to 0 in part B. Now, as far as the torque is concerned, now we actually have something else, right? Again, let's remember the equation for torque, I B times A times sine theta. Now, from the top view, I think it's easier to understand. Again, we're looking at the direction of the normal um, of the area and with respect to the direction of the magnetic field. From the top view, the direction of the magnetic field would be up, correct? It would look something like this. This is the direction of the magnetic field. Now, the direction of the area vector would be something like this. So what is the angle between the two? Obviously, this rotation is 30 degrees, which means the angle here is 30 degrees, which makes the angle between the two 180 minus 30 degrees, which is 150 degrees. Right. So then our theta in this case is 150 degrees. And well, the rest is pretty much the same, right? The current was given to us as 1.95 amperes, and the magnitude of the magnetic field is 1.5 times area, being again area of a rectangle. It's going to be length times width. So then length was 35 times 10 to the power of negative 2 meters, right? We did the conversion. 22 times 10 to the power of negative 2 meters. This is the area. Oops. I apologize for that. And then we have the sine 150. If we do the calculation correctly, what we get is 0.11 Newton meters for torque. Now it's time to determine the direction of torque. How are we going to determine the direction of torque? Again, it's the right-hand rule, right? So we're going to align our thumb with the direction of the area, along the direction of the area. And then rest of our fingers are going to be showing the direction of the B field. And then we're going to curl our fingers 90 degrees. From the top view, then, it's actually going to be towards us, the direction of the torque. So let's say the direction of the torque is going to be up the axis, right? So it looks something like this. If this is the direction of the torque, then what can we say about the direction of rotation? Because they're two different things, right? Direction of rotation, then, using again right-hand rule, it's going to have to be from the top view, it's going to have to be counterclockwise, right? Counterclockwise.